What we left off with on Wednesday, because I believe I was told this morning that today is Friday, is this idea of the E1. And the E1 is completely different to the E2. Okay? The E2 was everything happening at once in a concerted fashion. The E1 now is stepwise. So if you are being, and I should congratulate the soccer team for actually scoring 2 goals and winning a game. I'm sorry. They're now 1 and 99. It's great, isn't it? Well done. We're talking about the use, in this case, usually of acids to do this reaction, not bases now, and we're trying to differentiate between reactions in which everything happens at once and reactions in which things are stepwise. Now, in this stepwise reaction, we're going to see a carbocation get formed. That is parallel to the SN1 reaction. With the E2 reaction, that was parallel to the SN2 reaction, and at the end of today, when I finish 8, they'll all come together, and you'll have to start making decisions not just on SN1, SN2 like you did for the last exam, but for SN1, SN2, E1, and E2. Putting it all together is quite complicated. So on Wednesday, we started looking at this idea, and we introduced the concept of alcohols reacting with a strong acid. So if I were to write something like H plus here to abbreviate that, everybody should be okay with this. We often see this as a preliminary step in a mechanism to allow for a good leaving group. Alcohols themselves, the OH group is not a good leaving group, but if you protonate it, all of a sudden it can come off. So in that first step, we can protonate. And we've got to start thinking more expansively now, like chemists, to start understanding whether things will go backwards or forwards, certainly for later use. If that proton goes onto that OH group and you produce this guy down here, what does that remind you of? It's a 3-valent oxygen with a positive charge. What does it remind you of? Hydronium. And what was the pK of hydronium? Negative 1.7. So is that a strong acid or a weak acid? Strong acid. So it should be able to go backwards by giving its proton back up to go back to there. And you'll see this whole process is reversible. Every step makes sense in the forward and reverse direction, and we'll have to start worrying about how we get the product out. So this is a quick summary of what we did on Wednesday to get this stuff finished. Now, we set up a good leaving group, so it should make sense that the next thing to happen is a leaving group breaking off. In this case, water comes off, and we end up with a carbocation. Hold them in, you ready? What is the carbocation stabilized by? That's enough, thank you very much. It is stabilized by hyperconjugation. There is lots of it, so this is a good positive charge. But let's think again where this molecule of water is. This molecule of water is very close by, and if we're in sulfuric acid, water is the solvent. And in this case, again, water is there in great excess, so when you have a water molecule needed, there's one close by. It's not the same water molecule all the time, but there's plenty close by to be able to do whatever you want. So if I were to think about going backwards, what does the water have to behave as? What type of species? Nucleophile. It has to behave as a nucleophile. It has to go backwards and give us this species over here. So that should be okay, right? Because this guy needs electron density. This has electron density. Well, that's fine. That's to go back to the protonated OH group. To get to the product, what does OH2 plus have to behave as? Not a nucleophile, but what? A base. A base. And we know it can have both properties, so going after this proton here should be logical. It's not too far away. It's actually very close. And then giving these 2 electrons into the pi bond, and that should give us our alkene, and our alkene is stable. Now, we get water as the byproduct, but that's not really the whole story here. It's not really water that's being produced there. What is it? Look at what the product should be from that step. What should it be? Hydronium. It should be H3O+, okay? So that's important for several reasons. Number one, you can catalyze going backwards. We'll deal with that in chapter 9. That's a big process in which we can take an alkene and add to it and go backwards. But for now, we can recognize that this reaction should be speeded up by the presence of the proton, and that catalytic idea should be should round that out by recycling the catalyst. In this case, you get the catalyst back. So what you need to know now is that you can make this stuff. You can make it by deprotonating or dehydrating an alcohol, and it's a catalytic cycle. And also, it's completely reversible, unlike the E2s that we saw. So now we have to worry about how to produce this stuff. If this now has a lower boiling point than this stuff, because of the lack of hydrogen bonding, we can get rid of this. I think in lab next week you're doing the SN2, is that right? Somebody say yes. I think you are. And the week after you'll do the E1. So the E1, this will all come into play. We'll get rid of this stuff from the reaction mixture. If you have a flask, like one of those round bottom flasks that you deal with, and you clamp it onto a distillation apparatus, as the material is forming, you can distill it away. And Le Chatelier's principle says that if I remove some of this stuff from my mixture, what has to happen to compensate? It has to go in this direction. It has to drag some of this in this direction, some of this over here, and some of this over here. So if you continually do that, and you continually remove that product from the reaction mixture by heating it up and distilling it away, then you can make this reaction work in your favor. Even though that alkene maybe isn't as stable as the alcohol you start with, you can produce the alkene in high yield by being clever and removing it as you produce it. Then the equilibrium idea takes over, and you keep pushing it towards that molecule. All right? So we've got a whole bunch of ideas now in terms of things being reversible, things being not reversible, and you've got to keep on top of this stuff because it will get very, very tricky in that chapter 9. Any comments on that slide? That was just a quick look over. Stefan's going to say something.
Yeah, is the dissociation reversible?
The dissociation is reversible. That was the idea of putting that leaving group back on. If this guy goes in as a nucleophile and goes back over there, you cannot memorize this stuff purely. It is impossible, right? In fact, we don't memorize this stuff at all. Organic chemists, as you learn it, the principles start to come together and you can start to make informed opinions. Remember about drawing transition states? You should be able to draw transition states from what we learned, just from scratch, even if you haven't seen the reaction before. You should, certainly by next semester, be able to look at a process and decide, yes, that step in that process is reversible, without memorizing it. Colleen. Now, if you dissolve H2SO4 in water, what do you think you get? You think about what's the pKa of H2SO4? Negative something or positive something? It's negative a lot, right? And if you dissolve it in water and make H3O+, the pKa of H2O+ was what? Negative 1.7. H2SO4 is the stronger acid. So what do you think is favored, H3O+ or H2SO4? H3O+. Yeah? Now that's a good comment to make there because the people will get lost here. Yes, you're dissolving sulfuric acid up in water, but you've got H3O+, and we'll use that generically throughout the sequence to be able to show H+ being used. A lot of stuff here, but it's all starting to get, this is looking very biochemical. For those in the future, this is looking very biochemical in terms of different steps and reversibility. Well, Zaitsev's rule still applies. In terms of regioselectivity, you're going to get the more stabilized, more substituted product in each case. And this now is a little bit different in terms of the way we say this. In the E2, it was all about the transition states. And it was all about the relative energies of those transition states going to those products. And it just was coincidental that you get the more highly substituted product. Now it's reversible. So in a reversible situation, which do you get more of? The more stable or less stable material? More stable, that's logical. So this system goes backwards and forwards and backwards and forwards. And if you form some of this stuff, it can go backwards and it can give you the starter materials again. And eventually we end up with an equilibrium mixture. So this equilibrium mixture here really is a sort of measure of the difference in the energies of those molecules. The one on the left is a lot more stable than the one on the right. Why? The one on the left is tri-substituted, the one on the right is di-substituted, right? So you have an actual measure there of how stable these things are. Notice the temperature. When you do this reaction in lab, you'll heat it up for two purposes. Number one, to distill off the product. But what else? What else favors this reaction? Is it entropically favored or disfavored? You're going from one molecule to two, so it's entropically favored, right? And how do you enhance the magnitude of that delta S component? Heat it up, because T delta S. Just put it into delta G, and you find that that helps delta G be negative. So examples, this is where the practice comes in, and it's useful seeing what doesn't happen and what does happen. Again, I know you've got physics, you've got calculus, you've got golf to worry about, all that those other difficult classes. Keep on this stuff and don't get behind. In this bottom example, these two bottom examples, here I have a choice of going to this guy or this guy simply by doing the same process. How do I know it's E1? How do I know it's not E2? Acid. And I've mentioned several times now that pH will be a very useful criterion to be able to decide what's going to happen. If the reaction is basic, it's most likely to be E2 or SN2. If it's acidic, it's most likely to be SN1 or E1. Fairly simple way of dividing those up. Which of these two do you get more of, the left or the right? The one on the left, why? It's more substituted, right? This is tri-substituted and this is di-substituted. And in general, the idea is you want the alkene to be in the cycle. It stabilizes it more than if it's not in the cycle. And again, this is an equilibrium idea, so you will get some of both, but you'll get more of the more stable stuff based on substitution patterns. Down here, if I look at the possibilities here on a protonate, I can take a proton off here in the second step, and I can take a proton off there in the second step. As you practice material from this chapter, it's advisable to put those protons in. Look for the alpha position with the leaving group, and then put the beta protons in. If there's no beta proton there, you're not going to get elimination in that direction. So be careful. In this system, again, they look somewhat different to the ones above them, but it's actually the same problem. Which one do you get more of? The one on the right. So the simple E1s are no problem, but the issue with the E1 is it involves a carbocation, and carbocations can be a bit of a nuisance. There is stereoselectivity as well as regioselectivity. You must be happy with what they both mean. Regioselectivity is where is the double bond? Do I go to the left or the right? Different regions of the molecule, that's regioselectivity. Stereoselectivity is the possibility of having cis and trans in the alkene. So again, remember, this is a reversible process. So it will always give you more of the more stable stuff. Trans is favored here, why? It's more stable because the bigger groups are pointing away from each other. Simple enough. So that gives us more of this and less of this on the right, and we have now some ideas of how Zaitsev and the stereoselectivity ideas come into play as they did in a similar way in E2. Okay. So let's look at this example again. Where does the stereoselectivity come in? Thinking about mechanism, you've got acid here, so we'll protonate this thing. H3O plus, we can pick up H plus, lone pair from here, produce a good leaving group. That is reversible, as we've just said. Leaving group breaks off, as it does in the E1 and also in the SN1, and that gives me a carbocation. And that carbocation now is what shape? Flat, right? But at this point, I don't have a pi bond. I have an empty p orbital, that is the positive charge, but I don't have a pi bond yet. So what can I do that a pi bond cannot do? Rotate. So where does the trans come from? It comes from elimination, from this sort of conformation in which the two groups are pointing away from each other. You might want to say they're anti to each other, and that delivers the trans isomer. Whereas on the right, if I rotate simply, then this group, which are this group and this group in the alkene, will come closer to each other, and that will eliminate to give you the cis alkene. So it's all about the rotation that is possible in the carbocation once you get there. Of those steps, which is the rate determining step? The first one, the second one, or the third one? The second one, right? This is loss of leaving group. And as is typical here, that will be the rate determining step because you're going uphill to something unstable. In terms of the whole thing, this is the book's version of that. I'm okay. Now listen to this carefully. At this stage of the game, I'm okay with using that as the acid or H3O plus as the acid. There will be an argument coming up in the next chapter about the concentration of the acid and how that makes a difference in what happens. But right now, it's just H+. You put some acid in, and it's not HBr, and it's not HCl. Why not? What do they give you instead? They give you SN1 instead, right? Because they're good nucleophiles. The halides are good nucleophiles. In this case, we don't have a good nucleophile. And the answer to that is when this breaks off as O-, what can I do with it? Resonance stabilize, and so the conjugate base of this stuff is not a good nucleophile, so it doesn't get involved. And it turns out then that the best nucleophile, best base in this system is water from the solvent. So we can see now loss of leaving group, loss of H2O, defined using the definitions from the book, proton transfer in the first step, loss of leaving group in the second step, proton transfer in the third step, and that gives you the alkene. And it's a useful way of making double bonds. Well, we can do this with other substrates. And you'll see when you get to biochemistry, the E1 system and the SN1 system are also competing. Why don't I need an acid here? Why don't I need something in this mixture to help that leaving group break off? It's already a good leaving group. So you'll see consistency throughout this. We're not all of a sudden going to say that bromine's a bad leaving group. That's why we put it into a molecule usually, is to make it a leaving group. So in the first system, or in the first reaction here, we identify this as being either secondary or tertiary, and then we start looking at the product. And in this case, I'm using water. So what's the pH of this mixture? Is it basic, acidic, or approximately neutral? It's approximately neutral. Okay, it's neutral. If it was basic, what type of system do you think you'd have? What type of reaction do you think you'd get? E2. Yeah, base promotes E2. And there's a checklist coming up at the end of this chapter to try and keep those things straight. Now, you've got to be careful here. This happens in the synthesis of things like cholesterol in the body, all sorts of drug design syntheses, all sorts of biosynthetic ideas. What is different in the makeup or the skeleton of that product compared to where we started? Do you see a difference? Yes, I see two alkyl groups on this carbon, and when we get over to the right, there's only one alkyl group left. I only see one alkyl group on this carbon, this methyl group, and all of a sudden I've got two. That tells you, that gives you a huge clue. First of all, it's obviously a rearrangement, but rearrangements can only happen when you have a carbocation. You don't get carbocations in E2, you don't get carbocations in SN2, so all of a sudden you've narrowed this down to E1 or E2. Sorry, E1 or SN1. So what we've got to do here is form a carbocation. What is it about? Bring with you what you learned from the last material. What is it about this solvent that promotes loss of this leaving group? It's protic, good. Now what can a protic solvent do in a system? Hydrogen bond. So this, for the same reasons as in the SN1 reaction, will help the leaving group break off. It promotes loss of that leaving group. And then we have to think about this as a carbocation. It's secondary. So secondary carbocations aren't as good as primary carbocations, as tertiary carbocations, so therefore it needs to rearrange. And it rearranges in a logical way. I have two alkyl groups, so let's bump one across and end up with this, and that's a tertiary carbocation. For the same reasons this was good in an SN1 reaction. Now, in this last step, look at that carbocation. How many different types of beta hydrogen do I have? I have two beta hydrogens, but how many types? Just the one, because they're equivalent, right? This is symmetrical, so this side is the same as the other side. Oh, you're right, down here. You have one down there, but we're not going to talk about that because that's not going to give us the most stable product, right? In fact, if we do finish that through, what is the nature of this alkene? What substitution pattern is it? It's tetrasubstituted. And if you did take this off, what would you make? Disubstituted. So if there's a big difference between the stability of a tri and a di, what's the difference between a tetra and a di? Bigger, much bigger. So this will probably be maybe the exclusive product. So you've got to be very careful here. You've got to put an asterisk on this slide and remember that carbocations suffer from the problem of rearrangements. Now, when I say suffer from a problem, that means from my perspective as a synthetic chemist, where I try to design molecules and build them. Carbocations are a bit of a nuisance because they can rearrange. So as we get towards the end of this material and start putting it together for the end of the semester in chapter 12, we'll say that the E2 reaction is more useful to us because it's more predictable. We don't get those rearrangements, which you can get with carbocations. So be careful here, be aware of the rearrangement possibility. And how do you do that? You look at the product. You compare it with the starter material, and if they have different skeleton, they must have undergone a rearrangement. Okay, moving along. In terms of the mechanism here, this is just a different example. The first example we looked at there was a alcohol. It was a chloride. Here it's an alcohol. First step. Now, first question is, all of a sudden my conditions changed. Here it was neutral, here is it acidic. Why do I need acidic here? You need that proton to make a good leaving group. Absolutely. So we're starting to see some patterns now, some commonalities in these reactions. I protonate, I get to here. Loss of my leaving group gives me a secondary carbocation. Rearrangement, and you must look at some of the old material here. You must look at the old exams, look at the problem set. Some of these rearrangements are quite tricky. They involve cycles getting bigger. They involve all sorts of weird bicyclic systems reorganizing themselves. Have a look at those. If you can do those, you're in great shape. Get to this, all of a sudden we've got a proton transfer. Now, I'm not showing you an awful lot of detail here in terms of transition states, in terms of reaction profiles, but I do expect you to be able to come up with that material, those ideas. If you think about this first step, is it fast or slow? Fast, that's in there, right? That's a proton transfer is fast. So is that a high barrier or a low barrier? That's a low barrier, which you should be aware of. Which is the rate determining step? I've got 4 steps here. Which is rate determining? The second one, loss of leaving group. High barrier or low barrier? High. Look at this carbocation rearrangement. Fast or slow? Fast. Why? It's within the same molecule. It's intramolecular. You don't have to find anything else for this to happen. It's fast. And then we have this proton transfer at the end. Fast or slow? Fast as they all are. So without looking at that, you ought to be able to draw me, I would think, this reaction profile. And for those of you who are getting this stuff, draw me some transition states. Because if you understand the mechanism with the arrows, you also understand the transition states. Fairly straightforward. So I suggest you learn the mechanism in its pictorial sense, and then you try for yourself to draw the transition states and the reaction profile, and you'll be amazed how much you can do. You'll be surprised if you learn this properly, how much you can do. So let's talk about some other examples. Let's work our way towards the end of 8, which is all about deciding when what happens. We need some criteria to decide, I'm doing this reaction, not this reaction. Here I see an example in which a fairly simple alcohol gives a fairly complex product mixture. I seem to get 3% of this guy, 33% of that, and the major product is this. First off, you should look at the skeleton. That looks like a T-butyl group to me. Well, in this product, that seems to be kept. That seems to show up in the final product there. But in this product, no. I've lost an alkyl group. And alkyl groups just don't break off. It's moved someplace else. You'll notice here on the left that there's one methyl group attached, and on the right, all of a sudden, I have 2 methyl groups attached. That's just shouting out to you saying migration. And then all of a sudden, I get mixtures of these 2 compounds. Now, what's the substitution pattern here? Monosubstituted. What's the substitution pattern there? What about here? Tetra. So you can see where the numbers come from. And we'll decide that the minor product is because it's from the worst carbocation, which then quickly rearranges to give a better carbocation, which then eliminates to give you the 2 outcomes. So first step, fast or slow? Fast. It's a protonation. Go after a proton, pick it up. What's happening in the second step? Loss of a leaving group. You can see where exam questions come from very quickly, from different angles, ranging from fairly simple examples. Here's a mechanism, give me the steps. In terms of what's happening, is it a proton transfer, is it a rearrangement, whatever. But then the higher level questions are going to be, here's a start material, here's a product, tell me what happened. Draw me a reaction mechanism, all the steps in terms of what's going on. Is it reversible, is it not? Draw me a reaction profile, show me where the transition states are, what they look like. Not particularly easy. So the problem here is it's secondary, and again, of course, we can rearrange. We can think about this coming off from this guy. If we just eliminate from there, we're going to get some of this stuff, but obviously not very much, because all of a sudden this thing wants to rearrange to become this because it's tertiary, for the very same reasons we've seen a bunch of times. We now have to worry about the fact that we have a beta hydrogen here and a beta hydrogen here, and depending upon which one comes off, we go in this direction or we go in this direction. More of the same, I would suggest. Any comments? Cruikshank, are you well? Make sure Dodson's still awake. Okay. Engineers at the back, just hanging out. Just wait till PChem. Right. So here we go. We have developed in the past week, since the last exam, a fairly complex picture of what constitutes what we call an E2 and what constitutes what we call an E1. And the 2 and the 1 are the big clues. If you understand the SN1, the SN2, the numbers mean the same thing. In the E1, it's the same as the SN1, you get a carbocation with that as the rate determining step. In the E2, it's the same as the SN2 with no intermediate being formed, everything happening at once and bimolecular. So I want you to be able to do these things for next time round. Next time round is a ways away, Thanksgiving. But there's a lot of stuff between now and then. What are you looking for here? What criteria are you using to decide? And you can't do just simply, okay, it's DMF, therefore it's an SN2. That got you away with the second exam maybe, and that helped in that instance. But now SN2s and E2s both happen in DMF. And SN1s actually happen in DMF. They're just not as fast as in protic solvents. So we have to be more sophisticated and more careful here. So what we've got here is the E2 reaction. To go back and sort of summarize this stuff. The E2 mechanism involves a base. You must absolutely have a handle on what constitutes a base in this class. We have done a lot of acid-base chemistry. You should recognize that methoxide, CH3O-, is a base or a nucleophile. My friend Kotbu, right, potassium OT butoxide is either a base or a really poor nucleophile. Why is it such a bad nucleophile? It's too big, it's sterically crowded. So if you recognize the pH of your reaction that you're dealing with, you automatically have a device to start deciding what's going to happen. These bases typically are reactive or unreactive. They're very reactive. They are aggressive species. O-, always, I mean, I remember this since whenever I first started doing chemistry, maybe at 14, hydroxide is painful if you get it on your hand. OH-, a concentrated charge on an oxygen, is a reactive species because it will eat your hand off. Right? That's an easy thing to remember. So once we extrapolate that to the organic class, where we replace that H on hydroxide with CH3, that O- is still a little piranha, wants to go after things, right? Little missile going after things. So recognize that potassium, O-, right? Sodium plus O-. Those things are reactive species. They will not allow the ones to happen. They won't allow for E1 or SN1 to happen because they're so reactive, they're going after the molecule without allowing it to form a cation. That's absolutely key. So in this case, the E2, strong base. You've seen plenty of examples. You'll see more. Methoxide, T-butoxide, going after the substrate, not allowing a leaving group to break off, and giving you an alkene in one go, in one step. Well, the mechanism for that and the transition states, we've drawn these things in recitation this past week. We'll do more next week. This should be second nature by now if you've understood this stuff. We're not memorizing as much as we used to, I hope. We can start to apply the rules. In this example, even if this is a really good leaving group on this molecule, it doesn't stand the chance of leaving because the base is so reactive, it's the aggressive species going after the organic substrate. I'm looking for a beta hydrogen to go after. I form a pi bond, I lose my leaving group. Going through this, I should probably be careful here and put my double dagger symbol there to make sure it's a transition state. And we can see the bonds being formed and broken. And in this case, again, keep an eye on negative becoming delta negative. Neutral going through delta negative to become negative. It's the same principle applied to a different molecule, different system. How do I know it's E2 and not E1? Base. You're in base, right? That's the key. So we can then think about systems in which you mess things up, you mix things up. That's the confusing thing for many people in this class, is that all of a sudden on one day I'm saying this, and all of a sudden on the next day I seem to be saying something completely different when I didn't. I said in the past that maybe SN2 is all about primary systems and SN1 was all about tertiary systems, and that was fine. That made sense at that juncture. But now I'm saying that in the E2 system, primary, secondary, and tertiary all do E2s. Because it's not about the substrate, it's about the base being so reactive. All I need to do here is to consider this. This is a basic reaction mixture. Go back to the acid-base stuff. You've seen these things many times. Because of the sodium being positive, the O next to it is negative, that is a basic reagent, and it will instigate things like SN2 and things like E2, but not the ones. Now, why can't this do SN2? Tertiary. Everybody see it? Do everybody? Does everybody see that? Ryan, you okay? You're nodding vociferously. Yes, good man. Okay? Yes, it can't do an SN2 because it's too crowded. It's going to want to do something, so the E2 predominates, and that's what you get. Well, look at this guy. All of a sudden, we've changed one thing, and we get a different outcome. We get some of the E1, and we get some of the SN1. What has changed? What chemically has changed in that reaction? It's not basic anymore. In fact, what would it be? It's neutral. And if you're neutral, you don't have these little piranhas, these little base things, wanting to go after things. This is a quite stable molecule. Okay? So that's kind of laid back. It will wait for this molecule to do its thing. And in fact, doing its thing is a tertiary system, so what will it give me? Carbocation. Does this thing promote carbocation formation? Yes. Through what process? Hydrogen bonding. So it all adds up. It's consistent all the way through. So I'm not going to get just elimination chemistry because I don't have a strong base. The carbocation has time to form, and then it can go in different paths. If I get a carbocation for both the E1 and both the SN1, it should make sense that I should get some of both. In some, you're getting the water behaving as one species, in the other, it's behaving as something else. To get to the SN1 product, what does water have to behave as when it attacks the carbocation? Nucleophile, good. To get to the E1 product, what does the water have to behave as? Base. And we've been saying since we started this thing that a base is a nucleophile is a base. So it should add up now that you get both those compounds. This is where it all starts to come together. Like, wow. Everybody will change their majors to chemistry, and everything will be good. So, science classes are full of these tables and full of these charts and all this data. We're the geeks, and we've been spending our lives looking at these things, and we just sit there and go, wow, cool. And we have to get you to that point where you look at that chart and go, cool. Joe, you're almost there, I think. Yeah, some of you are almost there. But you should look at this thing and start to apply what you know. There really isn't anything new on this chart that we haven't seen. It's just a compilation of bringing it together. And then the challenge for you lot, sitting there as new people absorbing this stuff, is to understand it and hopefully appreciate it. So I'm looking at examples over here. We've said several times now that if you have HI, HBr, HCl, you have a good nucleophile, right? At some stage in that game, you have a decent nucleophile. So if this is brought in as sodium chloride, Cl- is good, I- is good, Br- is good, as nucleophiles. They favor the SN2 type processes. If you look at this guy here, good nucleophile, good nucleophile. These are all good nucleophiles. So maybe in a system that's accessible, they will allow for substitution bimolecular. But then we get into the middle here. And we've seen hydride a little bit, very powerful base. We haven't seen these two down here. The names are horrendous, which is why we abbreviate them. DBN and DBU. DBU is something we use a lot of in my lab. And it's basically there. It's a base. But what do you think the property of all this stuff? Why do you think we have all this stuff here? What's that going to do to the molecule? Makes it big. So that is said to be a non-nucleophilic base. It's the same as Kotbu, but it's neutral. It is a non-nucleophilic base because it's so big, it tends not to behave as a nucleophile and prefers to behave as a base because protons are accessible. It also allows this stuff to be soluble in organic solvents because you've got all that organic material right there. So I wouldn't worry about memorizing those names, but you might be aware of those structures. Just look at the lone pair here. They're both basic. And the superstructure, all the organic stuff, is there to make it big. Those are going to be bases. Those are going to give you what? E2 or SN2? E2. And if they're strong bases, what do they give you? Do they give you E2 or do they give you SN2? Strong bases and they're big. E2. And what about allowing for things like SN1 to happen? Probably not if they're strong. They're in a hurry to react. So now we move over to things that are more comfortable. We've seen these guys before. And we use these things a lot. You know, the nice thing about these things over here on the left is that they're soluble in organic solvents. Sometimes these things are not because they're salts, and we have to play this game of compromise. Now, if I draw a line down here, those are essentially the same thing. They are O minus localized charge on O. If you wanted to do an SN2, if you had a marginal system, and you wanted to prefer the SN2, would you use this material on the left or this material on the right? On the left, because they're small. If you want to maximize your outcome of an elimination process, what do you use? The one on the right. If you want to maximize your amount of the less favored alkene, and the less favored alkene will come about from taking off the proton maybe more accessible, which one would you use? The one on the right, because it's big. We've covered all that stuff. We've done all that stuff in the past week. Now it's your job to go back and sort it out, get it organized. Those flashcards will help out a little bit, I think. So now we have to identify the mechanisms that can happen. What are we looking for here? What criteria do we have to decide when a reaction is going to give what pathway? So all this is based on observation, all this is based on experiment, but from those experiments, scientists have come up with some pretty good rationales for why this works. Deciding upon whether it's a good nucleophile, deciding upon whether it's a good leaving group, whether it's a good base, whether it's big, things like that. So in this example, we're trying to identify, under these conditions, reacting with these types of substrates. So these types of substrates will have a primary system with a halide attached, a good leaving group, secondary with a good leaving group, and tertiary with a good leaving group. Now, if these things are good nucleophiles but not particularly good bases, what do they favor, the S or the E? The S. Right? They're not great bases, but they are good nucleophiles. So why do we get exclusively SN2 for a primary system? It's accessible. This is the language we've been building. This is what I want you to use. It's accessible. A primary system is easy to get to at the electrophilic carbon, so the SN2 should be good. Now let's take a little tangent here. Why do you think SN2 is preferred to E2? Why do you think the substitution product is preferred compared to the alkene? It's more stable because it's all single bonds. It's all sigma bonds, whereas in the double bond you have a pi bond, which is weaker. So you want to go this way if you can. The problem is that sometimes you have to divert. Okay, reasonable? Not controversial? If there's anything controversial, let me know. When's the next soccer game? Who against? Who are they? Are they any good? You've said that all semester. Now, move to the secondary system. What is happening in that secondary system? Really, what's happening? I went from a primary to secondary, and eventually I'm going to go down to tertiary. What is happening in my secondary system? We're getting more crowded. We are becoming more crowded. So in this example, with a secondary system, I am looking at now some SN2, if I can get to the electrophile, but I'm getting some alkene. Why am I getting alkene here and I didn't get it in the primary system? Because the nucleophile is having a harder time getting to the carbon it wants to attack, and so some of it diverts. Because we have the second pathway now, the E2, in which the proton is attacked at the beta carbon, and we get some elimination. So that's why that comes in. I'm sorry, my bad. Hello? Are you looking for someone? Not here. I know that for a fact. Okay? Sorry. Let's do that again. Secondary systems. Okay. It's just when people who don't recognize walking into the classroom, it's like, oh crap, here we go. The secondary system is going to have a choice. Now let's remember the context here. SH minus is not a particularly good base, Br minus is not a particularly good base, right? So we're going to get this problem here where we get some SN1 and SN2. You might get some E2 as well, depending upon how basic the reagent is. What I want to summarize for that is that this is not a particularly good system. What we're trying to develop between now and the end of the class, right, to lead us into the second term, is to be able to put this stuff together to be able to build molecules. If you wanted to build a molecule, you probably would not use this type of chemistry because you get these mixtures. These competitions between mechanisms are not synthetically useful. So we'll see now if we move to the tertiary system. we're going to talk again about these nucleophiles. Good nucleophiles, not particularly good bases. So now I have a possibility of SN1 because it's a tertiary system. Why not SN2? Because it's too crowded. So we move now to the SN1. So you can see, and I think we covered a bit of this in the substitution chapter, in which the SN1 and the SN2 compete, especially when you get to the secondary carbons. So let's summarize that. Useful, yes. Useful, yes. But what's the caveat at the bottom? Why is a tertiary system not so great if it forms a carbocation? What can carbocations do? They can rearrange. That's the asterisk. That's the limitation there. So now we move on a little bit. Let's develop into chapter 8 so we can get out of this today. On the left-hand side, we are now using molecules that are simply basic. And if I had to include one into here, what would I use? Base only? Give me something that I might use. Something else that's not on that slide. DBU, or the other one, my favorite? Kotbu. Okay? These guys aren't very nucleophilic at all. So this is where I said getting into this chapter is confusing because of the fact that we have primary systems doing E2, secondary systems doing E2, tertiary systems doing E2. And I want you to understand this. This is the take-home from this chapter. In the primary system, what would we rather do? What's the better outcome, the SN2 or the E2? The SN2. Why can't I typically do an SN2 here? Bases are very crowded, and also they're very strong. They prefer the E2. Move into the secondary systems. We're now looking at systems that are a bit more crowded. Should that favor an SN2 or an E2? E2. Why not SN1? Why not E1? Too basic, right? You recognize these things as being highly basic. They're not going to allow the carbocation to form. Down to the bottom, tertiary system. Why no SN2? Too crowded. Why no E1? Base is too strong, right? Base is too strong is not going to allow for an E1 to happen. Why not SN1? It's a tertiary system. Why can't I do an SN1? The base is reactive and does the E2 instead, right? And it's big, so it can't attack to do that type of thing. It does not allow the carbocation to form. So don't get lost on these charts. These charts are just trying to summarize and check that you know what's going on at the end of the chapter. Now here we get into some problems. All of a sudden now, if I have the intermediate guys, what is different? Let's say this is CH3O minus. These can be problematic. What's the difference between this material and the one on the last slide, the Kotbu stuff? The size, right? This one is tiny compared to the other one. So now I've got this problem where a primary system gives me some E2, and it also gives me mostly SN2. Why do I get more SN2 than E2? The system is more accessible, and also the product is more stable, and the transition state getting to it is more stable. Now down here, all of a sudden it switches. This will cause you nightmares if you're not keeping up. In this case with the secondary systems, the E2 is starting to become the major, and the SN2 is starting to become the minor. Why do you get less SN2? More crowded, less accessible. You're going to go for the beta protons instead, and so that's why we get more of that stuff. And then down at the bottom, why do I exclusively get this as the E2 product? You can't do an SN2 because it's too crowded, even though it's a small nucleophile. And why can't I do an SN1 or an E1? It's basic, and it's not going to allow that to happen. If you're going to listen to a lecture after, on the internet sometime this weekend, this is a good one to do because it's very confusing. Last one. Okay? Then a few more examples, and then I'm done with 8. We really need to get a handle soon on this idea of why we use this subject, what it's used for. Yes, it underpins a lot of the biochemistry you'll have to do in the future for many of you, even if it's not here or someplace, maybe someplace else. It also underpins a lot of the synthetic stuff we have to use as chemists in the polymer industry, the paint industry, the fine chemical industry that will introduce or interest the engineers, people who have to do that thing on large scale. Some of these reactions are just not useful. They are not practical. It's a very practical science. It's not all theory. We have to try and use what we know to extrapolate into the future and into new systems and apply these things. So let's say at the top, in this example, when you have weak nuclear, don't memorize this slide. That's just pointless. But appreciate what it's saying. Because the type of question I might ask here would be, here's a system, it gives you 15 products. Tell me about this system. Right? First thing you'd say, it's not practical. That next thing you'd say is why. Separation is expensive, and 15 products, you've got 14 of them you don't want, it's a waste. And then you'll tell me why, from the principles we just talked about. So weak nucleophile, weak base really aren't much use at anything in terms of SN2s or E2s. You're going to get a bit of both, but it's not really that much use in terms of this not being a strong base. If you wanted to do an E2, you would use a strong base. That's a little shift that we haven't talked about yet. That is moving towards doing synthesis and making things. You need to choose what to use. So this isn't practical, so we probably wouldn't do it in a synthetic lab. What do you make of this? 4 different products. What are you going to do with that? Probably not do it. This is just, that's not a reaction you would want to be dealing with. Unless you were the first person to look at it, and you then had to work out what all the products were, and then you had to say it was SN1, SN2, E2, and E1. You'd publish that stuff, and then people would avoid it, right? Because it's of no use in terms of a synthetic method. But down here, in the substitution reaction versus the E1 reaction, weak nucleophiles, weak bases allow for these things to happen. And I've just said, I think, in this class, that typically we don't do E2s. So, be careful here. We don't do E1s. We typically don't do SN1s if we can help it. We do the 2s. If you think about the SN2, it gives you one product. If it's an inverted product, great. You know the stereochemistry, all right, in the E2. And in the E2 product, you typically get one product depending upon what you want in terms of the base of the substrate. So some reactions just don't work. Some reactions are very useful, and some reactions are just a pain. That is summarized in this slide. Read it, don't sweat over it, but practice problems and start to see that if you go to these slides as you study, you'll see the differences. You'll see that this thing makes sense. Big bases typically don't give you substitution products. Small bases can, depending upon the accessibility of the electrophile. It's all the same stuff. Now, examples, once we've done that, this is just telling you that the most useful things you will see from now on, of course you're going to see it all because we have to test you on it all, but the most useful things you will see in terms of doing synthesis will be this type of deal where we do E's and we do substitutions. What you need to get over this weekend is the idea of pH. Is it basic? Yes. That gives me the 2s. Is it neutral? Yes. That might give me the 1s. Is it acidic? Yes. That usually gives me the 1s. Then it's up to you to know what to do with the materials. Examples, just to finish off today, and then we're out of 8. Homework due Sunday evening. What's happening here? What can happen here? Is it basic, neutral, or acidic? Basic. So what do we expect? The 2s or the 1s? 2s. So what we might expect to see is some of this. Some of the substitution product and some of the elimination product. Easy enough? This one down here. Basic or acidic or neutral? Basic. How do I know? Sodium makes the sodium plus here makes the O next to it negative. And so I expect to see some elimination 2 and some substitution 2 maybe. But then I've got this problem. Where are all these products coming from? What's the difference here? Cis and trans, which do you get more of? Trans, right? And you get some of the substitution product, but you also get some of these. Not a useful reaction in terms of being in the lab, but an interesting reaction in terms of why these things are happening, where they're coming from. Down here, careful. Acid or base? Base. Any substitution product? No, because it's too crowded. So what do we expect to see? Alkene from E2. So we should be getting that. This stuff is only difficult if you leave it until the last minute. But that's the idea with the quizzes coming up. There's a sit-down quiz in class next week in recitation on the E1 and the E2. There is a homework due on Sunday on the E1 and the E2. There's a quiz due next Wednesday night, E1, E2. So that just makes you study and keep up with this material so we don't get lost. Okay.